What is gravity? Of the fundamental forces of the universe, only one dominates every moment of our conscious experience: gravity. It keeps us close to the earth, raises and lowers footballs and basketballs, and gives our muscles strength. From a cosmic perspective, gravity is just as consistent. From the collapse of hydrogen clouds into stars to the merging of galaxies, gravity represents one of the few players that defines a broad view of the course of the evolution of the universe. In a sense, the history of gravity is the history of physics, but even after more than 400 years of study, the mysterious force still underlies some of the discipline's greatest mysteries. People have long speculated about gravity acting on everything from raindrops to cannonballs. Ancient Greek and Indian philosophers noticed that objects move naturally toward the earth, but it would take a flash of insight from Isaac Newton to raise gravity from an incomprehensible tendency of objects to a measurable and predictable phenomenon. Newton's leap, made public in his 1687 treatise Philosophiae Naturalis Principia Mathematica, was the realization that every object in the universe, from a grain of sand to the largest stars, attracts all other objects to itself. This notion united events that seemed completely unrelated, from apples falling to the earth, though this probably didn't inspire his breakthrough, but Newton did work next to an apple tree, to the planets orbiting the sun. He also attributed numbers to gravity. Doubling the mass of one object makes its attraction twice as strong, he determined, and bringing two objects closer together quadruples their mutual attraction. Newton packed these ideas into his universal law of gravitation. Newton's description of gravity was accurate enough to understand the existence of Neptune in the mid-1800s before anyone could see it, but Newton's law is not perfect. In the 1800s, astronomers noticed that the ellipse traced in Mercury's orbit was moving around the Sun faster than Newton's theory predicted, suggesting a slight discrepancy between his law and the laws of nature. This conundrum was eventually solved by Albert Einstein's general theory of relativity, published in 1915. Before Einstein published his groundbreaking theory, physicists knew how to calculate the gravitational pull of a planet, but their understanding of why gravity behaves this way made little headway compared to the ancient philosophers. These scientists understood that all objects were attracted to each other with an instantaneous and infinitely far-reaching force, as Newton postulated, and many Einstein-era physicists were willing to leave it at that. But working on his special theory of relativity, Einstein came to the conclusion that nothing can move instantaneously, and gravity's pull should be no exception. For centuries, physicists viewed space as an empty structure against which events played out. It was absolute, unchanging, and did not exist in a physical sense. The general theory of relativity promoted the transformation of space and time from a static background to a substance somewhat resembling the air in a room. Einstein believed that space and time together make up the fabric of the universe, and that this space-time material can stretch, contract, twist and rotate, taking everything in it with it. Einstein suggested that the shape of spacetime is what generates the force we perceive as gravity. A concentration of mass or energy, such as the Earth or the Sun, bends space around them like a rock bends the flow of a river. When other objects move nearby, they follow the curvature of space, just as a leaf can follow the vortex around a rock, although this metaphor is not perfect, because, at least in the case of planets orbiting the Sun, spacetime does not flow. We see the orbits of planets and apples fall because they follow paths through the distorted shape of the universe. In everyday situations, these trajectories follow the force predicted by Newton's law. Einstein's field equations of relativity, a set of formulas that illustrate how matter and energy warp spacetime, gained recognition when they successfully predicted changes in the orbit of Mercury, as well as the bending of starlight around the Sun during the 1919 solar eclipse. The modern description of gravity so accurately predicts the interaction of masses that it has guided cosmic discoveries. American astronomers Vera Rubin and Kent Ford noticed in the 1960s that galaxies rotate fast enough to bounce off stars, like a dog shaking off drops of water. But because the galaxies they studied weren't flying away from each other in different directions, something seemed to help them stick together. Rubin and Ford's careful observations provided convincing evidence supporting Swiss astronomer Fritz Zwicky's earlier theory, proposed in the 1930s, that some invisible kind of mass accelerates galaxies in a neighboring cluster. Most physicists now suspect that this mysterious dark matter warps spacetime to keep galaxies and galaxy clusters intact. Others, however, wonder if gravity itself might be increasing on a galaxy-wide scale, in which case Newton's and Einstein's equations would need to be adjusted. Changes to the general theory of relativity must be really delicate, as researchers have recently begun to discover one of the theory's most subtle predictions: the existence of gravitational waves, or ripples, in spacetime caused by the acceleration of masses in space. Since 2016, collaborative research work with 3 detectors in the United States and Europe has measured many gravitational waves passing through the Earth. More detectors are emerging, ushering in a new era of astronomy in which researchers study distant black holes and neutron stars not by the light they emit, but by the way they vibrate the fabric of space when they collide. However, a number of experimental successes of general relativity overshadow what many physicists consider a fatal theoretical failure. The theory describes classical spacetime, but the universe ends up being quantum, or composed of particles, or quanta, such as quarks and electrons. The classical notion of space and gravity, as a single smooth fabric, clashes with the quantum picture of the universe as a collection of sharp little pieces. How to extend the prevailing standard model of particle physics, which covers all known particles as well as the other 3 fundamental forces, electromagnetism, weak and strong interactions, to encompass space and gravity at the particle level, remains one of the deepest mysteries in modern physics.